Lesson 4: Elements and Atoms. At its most fundamental level, life is made up of matter. Matter is any substance that occupies space and has mass. Elements are unique forms of matter with specific chemical and physical properties that cannot break down into smaller substances by ordinary chemical reactions. There are 118 elements, but only 98 occur naturally. The remaining elements are unstable and require scientists to synthesize them in laboratories. Each element is designated by its chemical symbol, which is a single capital letter, or when the first letter is already taken by another element, a combination of two letters. Some elements follow the English term for the element, such as C for carbon and Ca for calcium. Other elements' chemical symbols derive from their Latin names. For example, the symbol for sodium is Na, referring to natrium, the Latin word for sodium. The four elements common to all living organisms are oxygen, O, carbon, C, hydrogen, H, and nitrogen, N. In the non-living world, elements are found in different proportions, and some elements common to living organisms are relatively rare on the Earth. For example, the atmosphere is rich in nitrogen and oxygen, but contains little carbon and hydrogen, while the Earth's crust, although it contains oxygen and a small amount of hydrogen, has little nitrogen and carbon. Despite their differences in abundance, all elements and the chemical reactions between them obey the same chemical and physical laws, regardless of whether they are a part of the living or non-living world. This table shows the approximate percentage of elements in living organisms, humans, compared to the non-living world. To understand how elements come together, we must first discuss the element's smallest component or building block, the atom. An atom is the smallest unit of matter that retains all the element's chemical properties. For example, one gold atom has all the properties of gold, like its chemical reactivity. A gold coin is simply a very large number of gold atoms molded into the shape of a coin and contains small amounts of other elements known as impurities. We cannot break down gold atoms into anything smaller while still retaining the properties of gold. An atom is composed of two regions: the nucleus, which is in the atom's center and contains protons and neutrons. The atom's outermost region holds its electrons in orbit around the nucleus. Atoms contain protons, electrons, and neutrons, among other subatomic particles. The most common isotope of hydrogen is the only exception and is made of one proton and one electron with no neutrons. Protons and neutrons have approximately the same mass, about 1.67 times 10 to the negative 24th grams. Scientists arbitrarily define this amount of mass as 1 atomic mass unit, or 1 Dalton. Although similar in mass, protons and neutrons differ in their electric charge. A proton is positively charged, whereas a neutron is uncharged. Therefore, the number of neutrons in an atom contributes significantly to its mass, but not to its charge. Electrons are much smaller in mass than protons, weighing only 9.11 times 10 to the negative 28th grams, or about an 1800th of an atomic mass unit. Hence, they do not contribute much to an element's overall atomic mass. Therefore, when considering atomic mass, it is customary to ignore the mass of any electrons and calculate the atom's mass based on the number of protons and neutrons alone. Although not significant contributors to mass, electrons do contribute greatly to the atom's charge, as each electron has a negative charge equal to the proton's positive charge. In uncharged, neutral atoms, the number of electrons orbiting the nucleus is equal to the number of protons inside the nucleus. In these atoms, the positive and negative charges cancel each other out, leading to an atom with no net charge. Accounting for the sizes of protons, neutrons, and electrons, most of the atom's volume, greater than 99%, is empty space. With all this empty space, one might ask why solid objects do not just pass through one another. The reason they do not is that the electrons that surround all atoms are negatively charged. and negative charges repel each other. Atoms of each element contain a characteristic number of protons and electrons. The number of protons determines an element's atomic number, which scientists use to distinguish one element from another. The number of neutrons is variable, resulting in isotopes, which are different forms of the same atom that vary only in the number of neutrons they possess. Together, the number of protons and neutrons determine an element's mass number. We can disregard the small contribution of mass from electrons in calculating the mass number. We can use this approximation of mass to easily calculate how many neutrons an element has by simply subtracting the number of protons from the mass number. Since an element's isotopes will have slightly different mass numbers, scientists also determine the atomic mass, which is the calculated average of the mass number for its naturally occurring isotopes. Often, the resulting number contains a fraction. For example, the atomic mass of chlorine, Cl, is 35.45 because chlorine is composed of several isotopes, some, the majority, with atomic mass 35, 17 protons and 18 neutrons, and some with atomic mass 37, 17 protons and 20 neutrons. Isotopes are different forms of an element that have the same number of protons but a different number of neutrons. Some elements, such as carbon, potassium, and uranium, have naturally occurring isotopes. Carbon-12 contains 6 protons, 6 neutrons, and 6 electrons. Therefore, it has a mass number of 12, 6 protons, and 6 neutrons. Carbon-14 contains 6 protons, 8 neutrons, and 6 electrons. Its atomic mass is 14, 6 protons, and 8 neutrons. These two alternate forms of carbon are isotopes. Some isotopes may emit neutrons, protons, and electrons and attain a more stable atomic configuration, lower level of potential energy. These are radioactive isotopes, or radioisotopes. Radioactive decay, carbon-14 decaying to eventually become nitrogen-14, describes the energy loss that occurs when an unstable atom's nucleus releases radiation. The periodic table organizes and displays different elements. The table groups elements that, although unique, share certain chemical properties with other elements. The properties of elements are responsible for their physical state at room temperature. They may be gases, solids, or liquids. Elements also have specific chemical reactivity, the ability to combine and to chemically bond with each other. In the periodic table below, the elements are organized and displayed according to their atomic number, and are arranged in a series of rows and columns based on shared chemical and physical properties. In addition to providing the atomic number for each element, the periodic table also displays the element's atomic mass. Looking at carbon, for example, its symbol, C, and name appear, as well as its atomic number of 6 in the upper left-hand corner, and its atomic mass of 12.01. In conclusion, the periodic table groups elements according to chemical properties. Scientists base the differences in chemical reactivity between the elements on the number and spatial distribution of an atom's electrons. Atoms that chemically react and bond to each other form molecules. Molecules are simply 2 or more atoms chemically bonded together. Logically, when 2 atoms chemically bond to form a molecule, their electrons, which form the outermost region of each atom, come together first as the atoms form a chemical bond. See you in the next lesson.